Hi, welcome to MEEN 221. Today we are going to talk about special kinds of rigid bodies which are called two-force members or two-force bodies. Okay, so let's see what these two-force bodies are and why we care about them. So we are going to show some experiments to show how rigid bodies that are subjected to forces at only 2 points will behave at equilibrium. So at the end of this demo, you should be able to draw the free body diagram of any two-force member. This sounds easier than it is because people get tricked by this a little bit. Write down the reason why we can eliminate such bodies from equilibrium consideration. So what it is that the big advantage is we will be able to eliminate such bodies. So basically what it is that suppose I have a body like this and I have forces that are acting at only 2 points, A and B. This will be called a two-force body. And the free body diagram for this kind of thing is actually quite simple, and it's so simple that equilibrium and other things can be automatically met, so we don't have to really struggle very much. Okay, so we'll talk about this in this class. So first let's talk about what is the definition of a two-force member. Any body in which forces can be idealized to act at only 2 points on the body. So if you have a body like this and you have force F1, force F2 and then weight of the body, this is not a two-force body because forces are acting at 3 points. But if you idealize it to say that there are only F1 and F2 like that, then this is a two-force body. Forces acting at only 2 points. That is the basic idea. Okay, so let's see what these things look like and where do they occur. So I want you to see, here is an example of a two-force body. Can you see forces will act here and here, and so this is a two-force body. Can you see the two-force body here? Right? This is not a two-force body because there are forces acting here, there's force acting here, there's force acting here. That's not a two-force body. This thing is not. Now if you look at this whole structure, you can see lots of two-force bodies. Can you see that? All of them are two-force bodies all over the place. Okay, so I want you to understand that a typical two-force body will have exactly 2 places where things can be connected. Nothing can be connected anywhere in the middle. You cannot connect anything here. Okay, so typically all the hydraulic rams and things like that are typical. Here this farm tractor with this back with this bar in the back is a two-force body. Excellent. Okay, so what do we gain? Why do we care about them? Because they are widely used. They are very efficient at transmitting forces. So if you apply forces at only 2 points, that's the best way to transmit them. If they are present, they can be used to simplify the free bodies by a lot. So that's nice. You can get the results even if you don't recognize them. Suppose you didn't realize it, nothing will happen. This is a shortcut. So this is useful because it will simplify the results by a lot. So you get quite a bit for a small amount of effort. That's why we are putting some effort into this. Okay, so now look, we have first example. I have some object and I have two strings here and I'm going to pull them by equal and opposite forces. Notice that the forces are parallel. So what do you think will happen if I pull along the black arrow? So suppose I pull like this and I pull like this. What do you think will happen? And do you think it will go on spinning? Do you think it will stop? What do you think will happen? Before you watch the video, I want you to stop, think about it, write down the answer or maybe draw a sketch and see if you are right. Okay, I want to show you what's going to happen. This is not very challenging. I mean, I'm not saying, there's no trick here. So let's pull it. Right? What I want you to see is at equilibrium, can you see these two things align themselves? That's the big deal. Okay, you can see that they align themselves. That's the big deal. And this is a two-force body because there's a force applied here and then there's a force applied there. You can see the line, and the idea is that when I started out, there was a net torque on the body. So the body rotated until the net torque went to 0, and when there was no torque, the strings were aligned and they were aligned along the line connecting the 2 points. The 2 points where the forces were acting. If you don't realize this, if you're not sure about this, go back, look at the video and come back. Okay. So now I have forces which are sideways. That is, there's a force this way and there's a force that way. Clearly there's a net force pointing somewhere like that. And because the two forces are not acting actually along the same lines, so you might find a net torque, you might rotate. So if I pull these two strings, what do you think will happen? Okay, so let's see what will happen. Watch, I'm going to pull them. There, pull, pull, pull. Did you see? It went all the way until the thing got aligned like that. Right? So in this case again, that initially there was a net force and moment, and so it started to translate, and once it started to translate, it started to rotate also, and until the forces became aligned. So the forces have to be aligned along the point of contact. Now I want you to try this yourself. So I'm going to pull these two things. I want you to tell me which way will it align. Will it go like this? Will it go like that? And here, do you think it's going to go somewhere until this thing gets to the middle? What do you think is going to happen? Make a guess. Put it down. Show me what will be the equilibrium position for these two things, where the strings will be before you look at the answer. So let's do this. I'm going to pull it. I'm going to pull it. I'm going to pull it. I want you to notice that it aligned itself along the line joining the two things. Now try this one. I'm going to pull it. Notice again, none of these things mattered, only the alignment mattered. Okay, so please remember, the only thing that matters is actually what is the force of the body. So what happens is this. When a body is subjected to only two forces, the forces will be aligned so that their magnitudes are equal. This has to be equal to that. Their directions are opposite. Can you see that? And the line of action is the same, and it passes through the point of action of the two forces. So it will go like that. And the line of action does not depend upon the shape of the object at all. It only depends upon where the forces are applied. A classic example is a bow and arrow. It doesn't matter, the shape of the bow doesn't matter. The string directly goes from one end to the other end where it's connected. Okay, so typical crossbow or any of these bows, the two-force member is very, very clear. That's the bow. Okay, got it? Very good. So the idea is, because of this, we can simplify the free bodies of figures. I'm going to show you an example where we can do this. So what happens is, the simplification proceeds in the following steps. Let's say we had this problem where I had this bookshelf. You remember this problem we solved the other day? So this is point A, and I had weight here W, and this is point B, and this is point C. Sorry, this is point B, this is point C, this is point D. So there's rigid body number 1, rigid body number 2. So if you look at it, the way we solved it last time was to draw two separate free body diagrams for the two rigid bodies. Now, because we know a little bit more, we can identify this body 1 is not a two-force body, because three forces. There's a force at point A, there's that, and they're acting at three different locations. Body 2 is a two-force body. So because it's a two-force body, I'm going to eliminate this, and I'm going to redraw this like this. Pin joint here, weight here, and then at point C, I'm going to draw C, and then at point D, I'm going to draw C. And this angle is 45 degrees. Because that was the angle of the bar. That's the line joining D and C. So what happened is, I don't have two forces, I already know the angle, so I'll now reduce it to just one free body diagram rather than two free body diagrams, and then it will be much simpler. I don't have to solve for many unknowns. It's actually make my life much easier. So every time you see a 2-force member, you should jump for joy. Remove it, replace it with the force that's along the line joining the 2 points where the forces are acting, and then your life will become much easier. This takes a little bit of getting used to, but once you get used to it, you will see how much simpler things will be. Thank you.